So this is the practice questions from this past Friday's lecture, both about the mechanisms and the predict the reagents. So hopefully throughout this video you'll get a little bit of information on how to better approach these questions as well as understanding the mechanism behind them. So let's start out with this first one, which shows the cyclization of this ring in the presence of sodium hydroxide and water. And the first thing that you typically want to do whenever you look at any of these mechanism questions is you want to ask yourself, what is the transformation that's happening, and how can we make that transformation happen? In this scenario, we see that the oxygen that I have highlighted in red is the same as this oxygen shown here on the other side of the reaction arrow. We can also see that this oxygen is now connected to a carbon in the final product. That same carbon is highlighted in orange here. We can see that based on numbering these substituents, starting with the oxygen is 1, this carbonyl is 2, this carbon is 3, this one is 4, and the orange one is 5. Those are the atoms that make up our 5-membered ring here. And so if we're forming a bond between an oxygen and a carbon, especially one that has a leaving group on it, because notice that this bromine right here is considered a good leaving group. That means that in this scenario, we must be doing some type of substitution reaction. Since we're on a primary carbon, it makes it even more likely that we're probably doing an SN2. So that's what we'll write down here. We're probably going to be doing an SN2. The other thing to bear in mind is the reagents that we have available to us. When we take a look at this, we see that we have sodium hydroxide. And sodium hydroxide, whenever we think about that, it of course splits up in solution. It dissociates to generate hydroxide. In the case of what hydroxide is going to be doing here, it's not as though hydroxide is actually doing the substitution, but rather the hydroxide is going to be acting as a base. This should be pretty obvious considering when we look at our starting molecule, this functional group right here is a carboxylic acid. Of course, with the word acid being in your name and the presence of a strong base, this implies that we are probably going to see an acid-base reaction occur. And of course, whenever we're looking at any of our reactions, acid-base chemistry, for the purpose of OChem, is going to be one of the fastest reactions that we will see. So based on that information alone, it makes me think that at the beginning of this mechanism, we're probably going to see the acid-base reaction happen first. So what we're going to do is we're going to redraw the starting materials, because a good practice for any time that you're doing these mechanisms is to redraw the starting materials so that you can show all important atoms and bonds, as the instruction says right here. The important atoms and bonds here are going to be the bond between the oxygen and the acidic proton. We need to show that because we're going to be showing that proton being deprotonated by our base. So let's now draw in our hydroxide base, and let's show the reaction between them. Of course, with hydroxide being a base, it's going to be donating the electrons to that proton. The deprotonation is then going to be giving the electrons from the oxygen-hydrogen bond to the oxygen itself. This is going to generate an anion, right? That oxygen will now have a negative charge. And so what we've done between step 1 and step 2 here is that we have change the carboxylic acid oxygen that's there from a weak nucleophile to a strong nucleophile. Of course, an SN2 requires a strong nucleophile and a good leaving group present at the same time, and so this is going to be that point where we actually form that bond between the oxygen and the other carbon. So let's go ahead and do that. The oxygen will come in, do a backside attack, kick out the bromine in one step, and this, of course, will generate our 5-membered ring, because we've now formed that bond between the oxygen and that carbon number 5. And remember that whenever you're doing these things, it's usually useful to keep in mind what is forming and breaking in the reaction, so sometimes numbering here helps as well, because you'll notice that in our numbering, the 1, 2, 3, 4, and 5, we can say that we are forming the bond between 5 and 1, so in our product, the 1, 2, 3, 4, and 5, we should see that we did indeed form the bond between 1 and 5. And so that's the mechanism for this one. We generate that 5-membered ring, and there's nothing else to say. Let's do the second one now. So in this second one, we have somewhat of a similar scenario to the first. If we look at our reactant, we now have an interesting functional group. It's called a hydroxamic acid, but that's beside the point here. The important piece is that if we look at our reagents, one of them stands out as being a very strong base. This is sodium hydride. Sodium hydride in solution makes hydride, which is a very strong base. This means that, of course, we're going to be looking at this and determining what's going to be happening with our strong base. The other piece of information that we need here is what happens between the reactant and the products. In this scenario, we're going to once again do some numbering, because numbering is going to be useful. I'm going to choose the carbonyl oxygen as number 1, but you could choose any other atom that you care about, because one thing that we do know is that this ring over here, it doesn't change between here and here. The same things are still connected to it, so that's going to be completely useless for our numbering. However, these other atoms, 1, 2, 3, 4, are going to be necessary. And what we see between these is that the 1, 2, 3, and 4 are found right here in the products, but we also now have numbers 5, 6, 7, and then this oxygen, which we will call number 8. So where does that come from in our reactants? Well, it's not coming from the sodium hydride, and it's certainly not coming from the DCM. It must be coming from this epoxide along with the alkyl bromide on it. When we look at these, we can say for certain one thing, that is that the oxygen must be number 8. That oxygen of the epoxide, as we can see in the products, must be connected to carbon number 7. And carbon number 7 must be connected to carbon 6, and carbon 6 to carbon 5. So this carbon must be number 7. It's the only way that it can be connected to number 6. And then 6 can only be connected to 5 in this way. If you were to put number 7 where number 6 is, it wouldn't actually have the same connectivity. And so this causes a very interesting question whenever it comes to our reaction, which is how do we actually get our product to form? Well, we can see what we need to do is that we need to form a bond between 4 and 5. Right? So here's 4 and here's 5. But we also need to form a bond between 1 and 6. There's 1 and there's 6. And of course the remaining bond to the oxygen will be between carbons 7 and 8. So let's go ahead and let's start off this mechanism by seeing what happens in the first step, which must be acid-base chemistry, and then we can make some decisions as we get to the later steps. So let's go ahead and redraw our starting materials. Because once again, we typically want to redraw these to show those important atoms and bonds. In this situation, the most acidic proton is going to be on the oxygen, because as a reminder, when we think of acid-base chemistry, oxygen is able to stabilize electrons a lot better because it is more electronegative. So our hydride will deprotonate the oxygen, and it will leave us with an anion on that oxygen. So if we now redraw that as the anion, we can see there's that. If this were to react with our other reagent, you'd notice something a little interesting. When we talked about epoxides, we stated that they were less sterically hindered typically than something like a normal alkyl bromide because the epoxide has this eclipsing interaction between the hydrogens, and it leaves a lot of space on the backside. It typically is also true that the breaking of an epoxide bond, releasing all the ring strain, is much more favorable than something like attacking an alkyl bromide. So in reality, when we look at an epoxide reacting with a nucleophile, even if there's a primary alkyl bromide in the molecule itself, it's actually more likely that our nucleophile is going to attack the epoxide itself. And this is kind of interesting because our numbering scheme up here doesn't support this as an actual possibility. Our numbering scheme said this was 8, this was 7, this was 6, and this was 5. However, what we would see here is that the most likely option of what is going to happen is that this oxygen should attack our epoxide on the least substituted side, because this would be similar to a basic epoxide ring opening, and kick the electrons up here. Now, while this may seem concerning at first, let's see where it takes us to get a better understanding of what the product of this reaction is going to be. So in this scenario, we've now formed a bond between the oxygen and the carbon that was a part of the epoxide. We've also broken the epoxide open. So we have carbon number 7, which was right here, has now broken from the oxygen, which was number 8. Carbon 7 is still connected to carbon 6, and carbon 6 is still connected to the oxygen, which now has a negative charge because when we broke the epoxide open, the electrons were placed on the oxygen. Then we also have on carbon number 5, which would be on the end here, an alkyl bromide. So we're also going to draw that in right here. This is actually an interesting point in time because notice what we have here is that we have a strong nucleophile, which is the negatively charged oxygen, in the presence of a good leaving group, the primary alkyl bromide. And so because of this, the next logical step would be an intramolecular SN2. And this actually solves the problem that we had seen in our previous step. Because once we redraw this, we have an interesting intermediate on our hands. So once again, we have carbon 6 and carbon 5 are now connected to one another alongside with the bonds to the oxygen. And here's 7, of course with the oxygen being 8. But notice that this numbering scheme is the reverse of what we had seen previously. We previously had it labeled as, in this direction, 5, 6, 7, but now it's 7, 6, 5. So in reality, our original numbering scheme was incorrect. It shouldn't have been that this was carbon 7. Instead, if we rewrite this, we would have actually wanted to say that in the end, the way that these are connected, if we did actually label these as 7, 6, and 5, is on the product, we would say that this is 7, this is 6, and this is 5. And so with that in mind, we can now continue to figure out what the product is going to be. So now what we have to ask ourselves is how does oxygen, that is right here, that we had previously labeled as number 1, how does this connect to carbon 6? Well, this is clearly going to be an epoxide ring opening. For an epoxide ring opening, we're going to need a good nucleophile. In this situation, we've already used up the sodium hydride from this step. But what you'll notice, if we give ourselves another page here, is that there is a resonance form that actually allows this to happen. There is resonance with this nitrogen, where the nitrogen can donate its electrons to form a double bond, kick these electrons up to this oxygen, and we see that we have a carbon-nitrogen double bond. The nitrogen now has a positive charge. All of our other atoms are still attached up on this side. But we also have a negatively charged oxygen. So this is now a good nucleophile. One of the other things that you'll notice here is that if we're connecting 1 to 6, one of the problems that we're going to see is that why wouldn't we connect 1 to 5? Well, notice in this case, if this is 1, 2, 3, 4, 5, and 6, for 1 to connect to 6, that would give us a 6-membered ring. However, for 1 to connect to 5, despite it being labeled originally as 5, because this would be actually number 7, despite this being labeled previously as 5, this would actually generate a 7-membered ring due to the weird numbering system that we had not being entirely accurate. Whenever we ask ourselves the question about which one of these is going to be more favorable, it's always going to be the 6-membered ring. So even though 1 to 5 would typically be what we would follow the rules of, because this would be similar to a basic epoxide ring opening, the rules about formation of rings actually takes over here. A 6-membered ring is more stable than a 7-membered ring in terms of a transition state, and therefore it's more likely for us to form the 6-membered ring than the 7. So, with that in mind, the oxygen, which we have labeled as number 1, can attack the backside of number 6 and kick out that oxygen. This then gives us the exact connections that we need for this given product. So notice that this is our 1, 2, 3, 4, 7, because 4 is connected to 7, 6, 5, and that oxygen we considered number 8. Now, don't forget your double bond down here, the positive charge on the nitrogen, because now we have to clean up some charges. This is what the water was introduced for, because now that we have these charges in the molecule, all we have to do is balance those out to reach our final product, because notice in our final product, the nitrogen down here is neutral, and the oxygen is also neutral with a proton. So water, whenever it comes into this reaction, would be able to do an acid-base reaction to deprotonate this amine here, even though it's more of an imine with the double bond present. And this would give us the neutral nitrogen that's a part of that ring. And so now the only thing to do is to protonate the negatively charged oxygen. Of course, that reaction with the H2O has now generated H3O+. And so with that, the final step of this reaction can be deprotonating the H3O+ to give us our final product, which is, of course, that 6-membered ring with all of the fun atoms in it alongside that alcohol on top. So hopefully these give you a pretty good idea on how to do some of these mechanisms, and always make sure that you're counting, because counting these things out can be really beneficial in making sure that you don't lose any atoms along the way, as well as making sure that your connections make sense. Let's move on to the second part of this, which was some predict the reagents questions. Now, the approach to these questions is sometimes a little different than those that we do for predict the products, because in the products we're asking ourselves, how do the reagents work to get us to some type of product? In something like this where we're predicting the reagents, we're asking what reaction needs to happen and what reagents will allow that reaction to happen. So let's take a look at this first one and how we can apply these principles. So for this first question, we see that we start out with quite a lot of stereochemistry, along with a chlorine, and we end up with a double bond. Now, that double bond right there immediately alerts me to the possibility that this is going to be an elimination reaction. Because anytime we do an elimination, that's how we're forming these alkenes. Whenever we look at this and we ask ourselves about the elimination, keep in mind that knowing that it's an elimination still leaves us with two choices. Is it an E1 or is it an E2? The question about E1 or E2 can be answered in a couple of ways, because remember, the premises of each one differs based on which alkene they can form. For an E1 reaction, we know that this will always form the most stable / most substituted alkene. However, for E2, we would say this depends on the base. So we have to ask ourselves, is the alkene shown the most stable / substituted alkene, or does it depend on the base that's used? Well, looking at this alkene here, the first thing that I would say is that this alkene is a tetrasubstituted alkene. And a tetrasubstituted alkene is, realistically speaking, the most stable alkene we can make. So this is going to be very stable, but the other thing we have to check is whether or not this is E or Z. In this situation, we see that our aromatic ring, which is the largest substituent on that side, is opposite of the largest substituent on the other side, which is the ethyl group. So this alkene here is an E alkene. So an E1 reaction would work here. The other thing to notice, though, is you may ask, well, what if I did an E2, but I utilized a Zaitsev base to give me the most substituted alkene? Well, in this situation, that actually wouldn't work. Notice that the other thing about E2 is that if we look at what our leaving group is doing, our leaving group is currently on a dash. That means that in order for this leaving group to be eliminated, it has to be anti to the proton that is on the other carbon. Notice that proton is also on a dash. This is a problem, because if that proton is on a dash, that means that this bond would have to rotate in order to actually produce the final product of a Zaitsev E2 elimination. So, with that in mind, if you were to use something like sodium amide, NaNH2, along with, some solvent such as THF and a little bit of heat, let's say you went 50 degrees Celsius, you would not receive the E substituted alkene. Instead, you would receive the Z substituted alkene, where the ethyl group is on the same side as the aromatic ring. So in reality, this tells us that E2 is not possible here. The only option is E1. So for an E1 reaction, of course this would happen with some SN1, but the important part is that we are figuring out the final product. All we'd have to do is say something along the lines of a weak nucleophile and hopefully high temperatures. So in this situation, I would say that a very classical weak nucleophile would be something such as water, and then we can heat that to reflux at 100 degrees Celsius. This should do the job. So this E1 reaction would be appropriate to reach that product. For the second one, sometimes this type of reaction requires more than one step. This is going to be an example of exactly that. So notice in this situation, we're going from starting with an alcohol and ending with a thioether. This isn't something that we can do in one step because alcohols are not good leaving groups. And so because of that, that tells us that in order for us to substitute this thioether onto this molecule, we would need to actually take that alcohol and make it into a good leaving group. Okay, so that's the first thing we need to do. Make good leaving group. But here's the thing. Not every reaction that makes an alcohol a good leaving group is appropriate here. Remember that we have 3 different methods for making alcohols into good leaving groups. Method number 1 is we could use a strong acid. Method number 2 is we could do a tosylation. And method number 3, we could do a halogen substitution. The question is, which of these is appropriate? In order to know that, we have to ask the question of what is the stereochemistry in the final product? We'll notice that in the beginning, we're on a wedge. In the end, we're also on a wedge. This is a retention of stereochemistry. So it's not an inversion, but instead, it retains the original stereochemistry, which was the wedge. Now, at this point in time in organic, we do not know any reactions that maintain stereochemistry despite doing a substitution. And so because of this idea of retention of stereochemistry, it tells us that in order to retain that stereochemistry, we have to see 2 SN2s happen back to back. Because notice that the first SN2 would change the wedge to a dash. The second SN2 would change the dash to a wedge. So retention of stereochemistry for us right now tells us this is SN2 twice. So now we have to ask ourselves the question, which method of making the alcohol a good leaving group is appropriate for making this retention of stereochemistry occur? So it needs to be one that does an SN2. First of all, we can look at strong acid. Strong acid is a bad choice here because remember that strong acids do a mixture of SN1 and SN2 when on a secondary carbon. So this one is bad. It would give us mixed stereochemistry. The second one, the tosylation, remember that this doesn't do an SN2. The alcohol acts as a nucleophile and attacks the sulfur, which makes it into the tosyl group. So in that situation, if we were to tosylate and then do the SN2, all we'd be doing is changing the stereochemistry one time, and we would expect that product to have a dash for the thioether. So this would also be a bad choice. Halogen substitution, though, does an SN2 to replace the oxygen with the halogen first, and then we can do the other SN2. So let's look at this in terms of these reactions down here. We're going to redraw out that starting material, and we're going to look at what happens if we do a halogen substitution. One of my favorites for doing this is something like thionyl chloride, SOCl2. And remember in class we talked about SOCl2 being the way that you change an alcohol into a chloride in a single step, and it inverts the stereochemistry. So this is inversion 1. The second reaction that we need to do is we now need to substitute on the thioether. We can do that by using a strong nucleophilic sulfur in order to kick out that chlorine leaving group. So in this situation, I would say using something like sodium methylthiolate, NaSCH3, which, as a reminder, if we were to separate this piece because sodium is going to be a spectator ion, is just methylthiolate. This is a strong nucleophile. Now we just need a polar aprotic solvent, say something like THF, and we'll add a little bit of heat just to keep it interesting. So, in this situation, the second SN2 would occur. This would give us our new thioether that's substituted there, and this would be our second inversion. So, of course, inversion 1 plus inversion 2, this overall is what actually equals a retention of stereochemistry. And so that is how we would solve this last one. Remember when we're putting these in as two separate reaction steps, we would put the first one as number 1 followed by that parenthesis, SOCl2, followed by that second step, which we said was the sodium methylthiolate, some THF, and that relatively elevated temperature, 50 degrees Celsius. So that right there is how we solve these problems. Hopefully you learned a thing or two, and you can use this problem solving on the exam in order to figure out these types of questions.